Newton's universal law of gravitation. So this part 3 here is really about Newton hypothesizing the physical parameters that may describe this force of gravity that could be useful in working with the planets, but also perhaps every object out in the universe. And what he hypothesized and posed was that this invisible force, which is gravity between two objects, is proportional to two things. One thing is that it's proportional to the product of their masses. So let's say you have two objects and they're separated by some distance. The force of gravity between them is proportional to the product of their masses. So mass 1 times mass 2. Okay. And he also thought that the relationship was inversely proportional to the square of the distance between them. So the force of gravity is proportional to 1 over r squared. We're going to use r squared since your book does. We could use d squared. That's fine. And by the way, this fish thing that you probably know as alpha, which in some contexts refers to angular acceleration. In here, this case, when we see one variable alpha like m1 times m2, that alpha means proportional to. Okay, it doesn't mean equal. It means this. The force of gravity is proportional to m1 times m2, proportional to the product of their masses. So if I double mass 1, this whole thing doubles over here, and so the force of gravity between them doubles. If I double mass 1 and mass 2, that is going to be 4 times greater, 2 times 2, and so the force of gravity between them is 4 times as great. So it tells us something about the proportion, like how many times greater one thing happens when you change one of these variables. And what's in the denominator is an r squared. So we have a square in the denominator. We're going to do a whole lesson on something called the inverse square law that is going to govern how this works, because there's some little tricks that we can do to be able to understand this a little better. You can brute force calculate it, but whenever you have a square in the denominator, it's known as, well, an inverse square law. And that will be our study after looking at this equation. All right. Real quick though, if you were to double something in the denominator, double the distance between them, this radius, then the force would weaken by 2 squared or 4 times. If you would have the separation as 3 times greater, it would be 3 squared or 9. All right, well that's about as far as Newton got on this stuff. The ideas were revolutionary, but they still couldn't really use it in terms of the units available to them, because they needed to know something called the gravitational constant. It's a number that goes in front of the equation that makes it work with everyday units, so they can actually make the calculations and make the predictions that he was hoping to do and predict Johannes Kepler's, or predict the describe the reason why Johannes Kepler's planetary motion laws actually worked. So a century later, about 1798, there's another scientist by the name of Henry Cavendish. And he's really important for various reasons. Not only did he experimentally determine this value, this gravitational constant, using what's known as a torsion balance, he's the guy who actually discovered hydrogen. He isolated hydrogen and said, this is it, this is hydrogen. So he's a really prominent scientist in England in the late 1700s, early 1800s. And this is one of the things he did on behalf of physics. So it's a really important thing that we're going to look at, because it enables us to make the calculation, how much force is there between two objects that have mass. And that will be able to lead us to our original question, which is, where's that reaction force for an object that's falling towards Earth?